Hi, this is Steve, and welcome to another Tech Leader Talk discussion. This interview is part of the Space Tech Innovation event, where I'm interviewing space tech leaders and they're sharing the latest trends and key insights that you can use to grow your own tech company, whether it's space tech or non space tech. The event is free. You can register at spacetechinnovation.com to get access to all the videos, the edited transcripts, and an executive summary of each interview. Today, I'm talking with Hunter Williams. He's a specialist in space resource utilization, planetary surface technology development, partnership management, and space system design. When I originally interviewed Hunter Williams, he was working at Honeybee Robotics, which he discusses several times during the podcast interview. But since we recorded the interview, Hunter has moved to a new position at Lockheed Martin doing business development and lunar infrastructure. And during our interview today, Hunter discusses different types of planetary surface robotics, such as Mars vehicles and exploration systems. And he also shares information about lunar arrays, lunar power systems, and a lunar electrical grid, all things that are currently being thought about and being developed. So I'm sure you're going to enjoy this discussion with Hunter, and you get some valuable insights about innovation and especially innovating when you're creating products or systems that are going to operate in a really harsh environment like the surface of the moon. So let's get to the interview with Hunter. Hi, Hunter. Thanks for joining me on the podcast today.
Hey, Steve, thanks for having me.
Hey. So I know a lot about your background because we've been talking some beforehand, and I gave the audience a little summary of kind of your experience with things. But tell us your journey. Have you always wanted to get involved in space? How did you kind of land with the work that
Oh,
you're doing today?
sure. So when I was a kid, I definitely said, when people said, "What do you want to be when you grow up?" I said, "I want to be a robotic engineer." And uh, then for a long time, that completely went out of my mind. I was not an engineer for many years. I was actually an English teacher. I
Okay.
kind of fell in love with languages and traveled around to, lived in a few different countries, taught English and learned languages along the way. But I had this thing in the back of my mind, just thinking like, maybe we should be doing something else. And one day I had this burning bush moment. I was reading "The Moon is a Harsh Mistress" by Robert Heinlein, and I just fell in love with the idea that this is what we could be doing. We could be living on the moon. It wasn't super far future, hard sci-fi kind of stuff.
Yeah.
It was it was possible with the technology that we have, or possible with a very clear technology development
Yeah.
pathway, I suppose I should say, right? And so, yeah, I just said to myself, this is what I want to help get to. This is what I want to work towards. And the funny thing is, to be an astronaut, you have to be just the most perfect human specimen, right? Physically, mentally, everything's got to be great. So part of this journey for me has been thinking to myself, what can I do to lower the bar so that just people like me could maybe one day get up and actually do what astronauts do, live
Mhm.
in space, be engineers on the surface of the moon. So yeah, that's kind of what brought me to where I am at Honeybee.
Okay. And that is what you're doing. That's what we'll talk about some today. What's There's so much going on. I grew up back in the Apollo era, and there wasn't anywhere near the activity we've got today. There's so many different companies and so many different projects and ideas and things. What gets you most excited about all the different things going on?
Oh wow, I'm most excited about the the democratization of the lunar surface in particular, but space
Hmm.
in general, I suppose I could say. The ability for a startup or a small company with 100 people to be able to build something that will go to the moon is incredible. So I look at our partners like Astrobotic, uh, you know, Firefly. These guys are doing some incredible things. Intuitive Machines even is like so swinging. Like a lot of these guys have some great venture capital backing, and they have a team of amazing engineers. But even with all all the money that they have, which to your average small business would look impressive, when you compare it to the past, where it took a mega corporation like Lockheed Martin
Yeah.
to do anything like what they're doing, it is incredible. And then when you add into the mix that like we're directly competing with companies like your Lockheeds, your Boeings, your Northrops, uh, and actually winning, it just shows that NASA is paying attention and trying to build up the capabilities of these smaller companies. So NASA's still relying on its long-term partners, its big winners like
Mhm.
the big aerospace corporations. But they've opened up the playing field to accept people like us at Honeybee. So it's just so exciting because um, it's the ability to get to the moon from a small company, but also it's the ability for new engineers to work on their first flight mission, to lead a flight mission sometimes
Yeah.
even. And that's something that maybe people would have one chance in a lifetime in previous decades, and now
Mhm.
because we're doing these much smaller, much more risk tolerant missions. uh, yeah, it's possible for somebody with only a few years out of grad school to be able to take ownership of the entire project.
Mhm.
So it's an
That's
incredible time.
yeah, it's exciting. It's yeah, certainly something that hasn't been there in the past, and um, it's fantastic. I love innovation. I love new technology. So this is exciting times.
Oh
So
yeah, absolutely.
tell us a little bit about kind of what Honeybee Robotics has done. I know there's been a lot of maybe go back to a lot of the work that you've done with the rovers and things on Mars, kind of how you got your start, and then we can talk a little bit more about what some of the new projects are you're working on today.
Sure. So Honeybee started off as a fairly straightforward terrestrial robotics company. So we did like the animatronic signs for Times Square, the Coca-Cola sign. We did the first robotic bartender. So if you look up Honeybee online, you can find pictures of our our old robotic bartender that we made
I have seen
like
that.
okay, yeah, there you go, like 30 years ago. And then one day, we were talking with Steve Squires, who was involved with NASA at that point, and we said we want to build something for space. Our founders were really interested in space, but we're not actively working in the industry. So they said we want to build something robotic for space. So can you take a chance on us? And it turned out to work very well because that ended up becoming our rock abrasion tool. We got put on the Mars exploration rovers, and uh, yeah, the first sample of the inside of a Mars rock uh, came from a Honeybee robotics excavator.
Wow, very
So
cool.
what's it was very exciting because the many missions had tried before that. The USSR and the United States in the past had sent several landers and rovers to the surface of Mars, and it hadn't, for one reason or another, they had never actually reached beyond the dust and patina that covers the surface of Martian rocks. So a lot of the really interesting geology is inside the rock. It's not
Okay.
out there on the surface. So when we looked at the inside, we discovered by studying the geology of the inside of the Mars rock that there had been a complete water cycle on Mars in the past. That there had been flowing water on the surface. So
Well,
that kind of solidified for us. This is the direction that we need to be going. So we stopped quite a bit of our terrestrial robotic activities and just went full into space.
hmm, okay, it's interesting. What so what are you developing today? As that's you've done different Mars work. What kind of
Oh,
things are
sure.
you working on today?
So we were on all the Mars rovers in recent history. So we are still doing operations for Curiosity, and we're some of the pictures that you see of the Perseverance rover dropping its sample canisters for Mars sample return. Well, our witness plate assembly is on some of those sample canisters, and also we are the final step in the Mars sample return mission. So we're still actively building mechanisms for Mars and for Mars science. but we have branched out to other places in the solar system, and most of our flight projects right now, these very low cost, high risk missions that we talked about before, are going to the moon. So
Okay.
we have like I think 5 or 6 missions that are flying this year and next to the moon, and then we are also the only company that is on the sample handling and sample acquisition subsystem for the Dragonfly mission to Titan. So Honeybee
Okay.
is we're doing some of the exciting uh, Eclipse program stuff with the moon, but we're also keeping our feet in the hard science stuff with NASA and the rest of the solar system.
Wow. That sounds fun. And at the rate things are going,
Yeah,
a lot of
yeah.
opportunities for you. So I know this is a heavy duty question and you can talk about it for a long time, but how do you design for the kind of environments that you're operating in? Obviously, you don't have the Earth atmosphere. So obviously, did you learn about how to deal in a hostile environment from the initial work on Mars? And then is that helping you today with your current designs?
Great question. It's been really interesting to kind of mentor new companies who are looking at that exact question. Like
Hmm.
how do we build for space, especially if we are on a shoestring budget, if we can't go test at NASA Johnson or somewhere that has a big, beautiful chamber that gets down to very, very low vacuum. And the answer is we we test to uh, the uh, the extremes of what we anticipate encountering, but not in realistic material. So a lot of people, when they want to test in regolith, simulant regolith, the dirt of other planets, right, or other celestial bodies, I should say. When people want to test in that, a lot of times they'll try to go out and find the most chemically accurate, the most
Okay.
beautiful, amazing simulant. And what we have found is instead of just trying to find one really good one, we will look for stuff with geophysical properties that match all the different edge cases that we might find
Okay.
and test that. So what that means is we'll do things like we'll mix motor oil into sand. We'll test in uh, like snow cone machine snow. We'll test in glass bubbles from 3M that they use to make the oil sands more fluid whenever they're doing pipeline work. So we take
Okay.
all these different materials, and no one on Earth would say that the regolith of Mars is anything like 3M glass bubbles used for oil sands. But
Hmm.
it just so happens that in testing these edge cases, we are able to make really robust equipment.
Okay.
Similarly, we test inside vacuum chambers like from the get-go. A lot of companies they'll reserve vacuum testing, thermal vacuum in particular, for the last stage of development when they're like ready to go to space and they built everything up. What we do is we kind of play in the vacuum in some senses, which is kind of silly to think about, but uh, it really is like learning through play in some ways in the beginning stages of technology development, because you have to get an intuitive feeling for how the technology is going to work in that environment.
Yep.
And sometimes just using it in kind of unusual ways or ways outside of the specific mission profile help you understand what kind of problems you may run into and what to do when you do.
Hmm. Okay. Interesting. So, eh, what have you talked about this a little bit, but what have you learned from like collecting the samples and especially getting inside the rocks and getting and those doing that analysis from the work on Mars that you're using in the current spacecraft or your current designs? And not only how are you using it, but how has that, what have you learned there that lets you iterate to make the robots even better in this new version?
Yeah, great question. The surface of Mars is so interesting because it's like a billion-year geological record of the solar system, right?
Interesting.
And there is a certain amount of you know fluid flow across the surface, so there's a small atmosphere, and there is even some water that goes through a water cycle on the surface. It's a very different water cycle than what's on Earth, but it's still there. And there's dust that flows across the surface as well, entrained in that atmosphere.
Okay.
So it's not a perfect vacuum by any means. Um, so what we learned in dealing with that uh, kind of interesting and very different geology that forms whenever you have that kind of atmosphere is that um, you got to prepare for all kinds of different situations. So it's not like there's just one kind of regolith up there. It's like if you went looking for water in the Sahara, and you built an ice drill to drill into the ground, but you tested it in the Sahara, you may not know how good your ice drill is because you were testing in the wrong environment, right? Well, there are
Okay.
geologies that are as different uh, from each other as the Sahara and the Antarctic are, right? So it's a fascinating thing to work on. So one of the things that we found out is if you don't test to quite a few different geologies, then there's a chance you'll get stuck. There's a chance that um, you'll not be able to complete the mission. But also there are times where some of the geologies will be surprisingly helpful for sample collection. We have many
Hmm.
times been surprised how well our technology works in some areas, and um, in hindsight, we'll be like, oh, of course, it's because XYZ factor. But until you've tested that, you have no idea, right?
Yeah.
So we we have tried to train ourselves out of being like, of course, that's why it works like that, because you never really know until you test. So one of the things that NASA has told us is that our approach to testing, our approach um, to hitting these edge cases in geology is definitely one of the things that has kept them working with us. And we have found that it's funny buying a really big vacuum chamber that we can do dirty testing inside of, which is a rarity. Most people, when they buy a big vacuum chamber, they want to keep that thing pristine because they're expensive, right?
Yeah.
Um, but us doing this dirty vacuum testing has actually been a big part of us winning contracts because NASA knows that we're not going to have to go out and destroy somebody else's vacuum chamber. We're going to destroy our own, and we're used to destroying our own, so it's going to be okay,
Interesting. Well, and the fact that you mentioned earlier, you get the vacuum chamber involved in the process early, throughout
Mhm.
the early design, early issues, and yeah, rather than waiting until it's done and realizing, whoops, there's a problem here we didn't realize, and then you got to back up. So
Exactly,
a
and
more thorough testing.
exactly another thing that's taught us is we we have discovered kind of accidentally in some cases uh, a new kind of technology that would work by trying out some kind of off the wall things early in testing. So we don't have a lot of internal research and development money, but when we get an R&D type contract from NASA, sometimes NASA wants us to try out some different ideas and put together kind of a portfolio of different options for what we're going to be proposing to them or what we're working on for them to meet requirements, right? So what that's led to is things like development of our Trident drill, which was built from the ground up. It is not like we took a Black and Decker from Home Depot and spacified it. We we had to start from nothing and build it up.
Yeah.
So there were a lot of components where we cycled through a bunch of different design phases um, to figure out what would work. So what is going to get eaten up by the regolith? What is going to be able to withstand, of course, the radiation and the temperature environment, but also just operation when you're dealing with stuff that doesn't act like dirt on Earth, that acts like crushed glass, but that's hard as a aluminous ceramic. It's a very interesting
Yeah.
material, lunar regolith. So yeah, another interesting thing that we found is we noticed that in the pump down. when you're pumping down your vacuum chamber, a lot of times you'd move a lot of regolith accidentally, you know? So we said, what if we used pneumatics? Like, what if we used moving gas instead of a physical augering drill, right? So what if we kind of took a little straw basically and slipped it into the surface? And we found out that it worked really well. We could move a kilogram of regolith with 1 gram of gas. Incredible, right?
Wow.
So that ended up being a whole product line for Honeybee. It ended up being like half of what we're sending to the moon right now because, you know, figuring out that one silly little thing that pneumatics actually work really well on an airless body. So
Okay.
again, in hindsight, everybody's like, yeah, of course it works really well, but um, it took a little while to get there, you know.
Yep. There's a quote, one of my favorites from I think Peter Diamandis, talking about the day before uh, like commercial acceptance of an idea or somebody giving it validity. It's a crazy idea. It can be for years. Then overnight, it can be, oh, now it's the miraculous breakthrough.
Right.
So it's yeah, that hindsight's always clear. How do you do some of this testing if you're going to be drilling, excuse me, into asteroids, planets, moons, whatever, and we don't have that material on Earth? And suppose
Yeah.
it's something that's never been drilled into. How do you know what's in there? How do you know what you're going to be up against when you try and drill into it?
Great question. So two ways we do that. One way is what I said before, as far as like trying it out in a whole bunch of different materials that are not like what we're going to be drilling
Okay.
into, but that represent certain parts of what we'll be drilling into. And the other way is we work with boutique regolith simulant makers who have studied studied the asteroids that have fallen to Earth, have studied
Okay.
the spectroscopy data that has come back on asteroids and said, okay, this is what we think, this is the best, the best configuration, the best geology. And they grind stuff up, they mix it together, a whole bunch of different earth rocks, and come up with kind of a simulation of what we'll be encountering. But then
Okay.
you have the gravity question, right? How do you simulate gravity? And that's actually something that Honeybee has thought about for years, because with drop tower testing, you only get a little bit of time, a very short amount of time. With parabolic flight testing, you get a little bit, you get a little bit more time, but it's not minutes, necessarily,
Yeah.
as like you would need like tens of minutes, like you might need with an actual concept of operations, a realistic concept of operations to run equipment from end to end, right? So
Mhm.
what we've done, we've actually proposed to NASA tech flights, and we've won a few flights for microgravity and partial gravity testing in suborbital spacecraft. So in
Okay.
the Blue Origin New Shepard. So we have two projects right now with that. So one of them is for testing asteroid physics, and one of them is for testing molten regolith electrolysis bubble physics to mimic lunar gravity conditions. So
Okay.
it's fun, and it's definitely a little bit expensive, but the data that you get from that kind of suborbital testing or microgravity testing is really valuable.
Yeah.
So we we love the tech flights program. That's something that like I actually don't talk about enough. I feel like is NASA Tech Flights has done a ton of good stuff for Honeybee for our technology development process. So shout out to those guys.
Okay. And what are those exactly? What's that? The tech flights?
So the Tech Flights program is it's a NASA program. It's one of the NASA programs that is I think it's not talked about enough, and especially for small technology developers who want to uh, send stuff to the moon or send stuff into space and don't have a ton of money. It's a great one for that, because it's a risk tolerant program in many ways. That doesn't
Okay.
mean it's not safe, right? It's an extremely safe program. They care about the safety of their spacecraft or aircraft, whatever you're doing your testing in. But it means that they're willing to take on projects that need some technology development. They need to get over the hump, so to speak, get through
Okay.
the TRL valley of death, as they call it. So The program allows you to propose to fly on high altitude balloons, uh, terrestrial rockets like the old Maston. We tested on the Maston Zodiac rocket, to do sounding rockets, or like what we're doing is suborbital rockets. That's one of the big ones nowadays that is available through the Tech Flights program. So they give you a little bit of money for um, developing your technology to interface with whatever system, so building up the rack so that you can go into the parabolic flight uh, payload bay area, right?
Hmm.
And then paying for the flight itself. The majority of the money goes towards paying for the flight.
Yeah.
So yeah, we've had maybe 5 or 6 technologies go into NASA Tech flights, and so it's all terrestrial or like suborbital. It doesn't ever actually go to space, right? It doesn't get orbital. ISS stuff is a different program,
Hmm.
but it has allowed us to test out some of our technology
Yeah.
in various ways that we would never have another opportunity to do without that program.
Right. Okay. So with this testing and simulation, I mean, your robotic systems are, I'm imagining, part of a bigger system, a lander, a rover, whatever. Um, uh, how do you kind of manage that testing of your component, and then in with all the other teams or the other organizations that are working to put together the final product?
So I'll tell you a little story about that. We are working with the Japanese Space Agency with their Moon Mars Explorer mission (MMX),
Hmm.
and we are going to, or sorry, Mars Moon Explorer. I always get that flipped.
Hmm.
But MMX is going to Phobos, one of the moons of Mars, to do the first sample collection from uh, the Mars system. It's very exciting. Sample return, I mean to say, right? We're going to be bringing back a sample
Okay.
from Phobos. So very exciting. And in early days, when we were developing this pneumatic sampler for this system, we were working with the satellite bus, the spacecraft company that JAXA, the Japanese Aerospace Agency, had selected,
Hmm.
and we were trying to figure out, could we get on the foot, or could we, like, how close to the foot can we get? And they were like, we really want to make sure that you guys are not sandblasting all of our equipment on the underside of the spacecraft, all of our sensors and cameras and stuff. So a big part of that process was, yeah, figuring out what kind of code we're going to be able to send back and forth between our payload and the main spacecraft. How do we
Okay.
electrically connect? What kind of fault tolerance do we need to make sure that we are not passing along issues to the spacecraft? And then how do we make sure that our payload, which is a pneumatic sampler, is not just blowing dirt all over the rest of the spacecraft, right? So it was a big process of working together with those guys, and even there were times where the language barrier was something that we had to overcome, because it's the Japanese Aerospace Agency, and and a lot of those guys can speak great English, but when you start getting into like technical Japanese and technical English, the
Yeah.
language barrier can come back, right? So uh, yeah, it's just a fascinating process. But we do that every single time we're on a mission, generally because Honeybee is not going to be doing the entirety of the mission. We're
Yeah.
not building the main uh, spacecraft that's going down. We're not building landers, for example, right? So uh, creating a interface control document, working with the systems engineers on our side and their side, that's a process every single time. And it's an important one, because that's where safety comes in. So our boss, Chris Zagney, he has a tendency to say this, and it's funny. People a lot of times kind of look at him until it sinks in what he's saying. If you're building like a car, right? The reason the car fails is not because driving off the lot they forgot to install a wheel, right? The,
Hope not.
the
Yeah.
big right, the big things they're definitely going to have on there. Anything obvious is going to be a part of it. The problem is going to be maybe they left a screw off the oil pan, or maybe they tightened the screw on the oil pan too much and it got stripped and then it started leaking oil, right?
Yeah.
So the problem is going to be in a small process. The problem is going to be in a single, seemingly insignificant component. That is, and that's what always causes failures, is
Yeah.
something in a small, seemingly insignificant component. And that's why in spaceflight we spend all this time and money on the on the systems engineering, but also in the validation and verification. The checkout of the spacecraft before it actually flies. So yeah, we spend a lot of time and energy in that testing, but also in the integration with the spacecraft in order to make sure that at least we know that our payload is not going to be the thing that causes failure.
It's not your fault, but
Yeah.
okay. Well, you've got a lot of experience as a company doing that, because obviously the Mars systems that you're on already, you had that issue. You were a component of the overall lander rover system. Interesting. So before we started the recording, we were kind of talking about the speed at which things are changing, and some things that, at least when I was a kid, is like, that's so far off. That's just science fiction. It may never actually happen. And one of them we talked about is the getting a presence, more of a permanent presence on the moon, for humans. And you talked a little bit about the lunar economy, and maybe that there would actually be, the moon will have its economy, and kind of what
Mhm.
some of those initial products are going to be. Tell us what at least your thoughts are on that.
Yeah, definitely. So I'm the PI here at Honeybee for the vertical solar array project that we have.
Mhm.
And Honeybee has been working for many years on ice harvesting technologies. So what we think is going to be the first thing that's sold on the moon. There may be some regolith sales, for example. There may be some regolith that gets put into a trust for all of humanity or something. Um, so that's great. But what is a true commercial business to business sale? Something that's for not done with science in mind whatsoever, right? Something that's done on a purely economic basis, something that
Mhm.
is heading towards lunar permanence. Because the thing about science is great. I got into this because I love science, but science science is not self-replicating, right? Science uh, does not create a an ecosystem for survival. It depends on those things.
Yeah.
So science is the customer, not the provider of resources,
Okay.
which is the way it's supposed to be, right? That's because it's doing science. That's what it's for. So uh, we want to be the first to sell something on the moon from business to business, to be providing a resource to someone else on the moon. And we think that maybe electricity may be the first thing that we end up selling, because everybody needs it. The only two groups to have lasted for a full year on the lunar surface, right? USSR and China, with with their lander and the U2 rover, right? So when you look at that, when you look at how the United States has never had a long-term lunar mission, right?
Mm.
We put boots on the ground first, but we've never done long-term lunar science, right? The reason that we haven't is because we relied pretty much exclusively on primary fuel cells and batteries rather than rechargeable batteries.
Yeah.
We never landed with solar PV on the moon. So
Mm.
the United States wants to change that now. I think now is the time where everyone is agreeing that uh, we should be doing uh, activities that will have longer than 1 month to operate, right? So
Mhm.
Artemis base, even just talking Artemis base camp, they've been specifying that it's likely the base camp will be operational even when there are not humans there, right? That there may be robotic science going on,
Yeah.
and it's exciting because that means that there will be permanent power. So Honeybee is focusing on building up the potential for a lunar electrical grid, and we're starting with a power provision system, so with a vertical solar array, and we're building out from there. The next thing that we think is going to get sold on the moon is propellant. So if hopefully Viper and Prime 1 missions with the Trident drill, the Honeybee Trident drill, find water ice on the surface of the moon. That's what we're trying for in the near future. Then that is going to completely change the way that we view the moon as a resource.
Okay.
We are going to, as humanity, we're going to be looking at the moon as a potential refueling depot, and as a place where people can actually live. Because if the moon doesn't have water ice, then it is still possible to get oxygen from the regolith through processes like molten regolith electrolysis, which Honeybee has also worked on. But but ice also has hydrogen, so you can create both parts of a liquid hydrogen, liquid oxygen propellant system if you can find ice. So it's very exciting if that is there. Either way, we're going to be very happy with selling electricity at the very least. And one of the things that I think it's really important to discuss whenever we do talk about these resources is that sometimes the imagery that comes to mind is like strip mining and a lot of the terrestrial processes that are that are somewhat controversial, right? There's no possible way for us to do things like that on the moon. And in fact, we're going to be moving very slowly and only taking small amounts of resources from the moon because the rockets are just not there. Like if I had 1 million rockets in my back pocket that I could send to the surface of the moon to refuel, that would be a different story. But we only are launching, one SLS every how many years, right? So anything that comes after, when you look at Starship and New Glenn, some of these rockets that may be making it to the surface, and especially when you look at the Blue Origin rockets that are made to be refueled, then you can start talking about, okay, how much is Blue really going to be building, and how much are they going to need? And the answer is one single crater, even if it has a very low weight percentage of water, even if the water is only in the first meter of regolith and it's completely dry all the way down below that, it could still take a century to use up the ice in one single crater.
Okay.
So we think that what's very likely is humanity is going to use the moon as a stop on the way to, say, the asteroid belt, to other places in the solar system that are extremely rich in water and metals and carbon. And so we will preserve the moon for future generations. We will not be using resources willy-nilly, and it will be kind of our cradle for the rest of the solar system.
Interesting. Well, it is. I mean, these topics when I was a kid, that didn't even talk about it that much. And nobody was thinking even that far ahead. We'd gotten to the moon, but it's interesting. It's some exciting stuff. Well, time's about to wrap up here. I love talking with you. What's ahead for
Great.
you? What's ahead for you and your team in the next year or so?
Well, we are very excited about the Mars sample return. So that's kind of a new thing that we've been working on. And so that's going to be dominating our minds quite a bit. But as far as new business development stuff, I hope that your listeners are following Honeybee, because we may have some big announcements coming up in the next year about specifically about a lunar grid. That is one of the things that we're working with certain partners on right now, that if it all comes to fruition, then we could be talking more seriously about that. There's a lot of exciting lunar permanence type of activities that are going to be announced in the near future. So yeah, stay tuned. Hopefully it's all going to happen.
We will. I will certainly be watching and excited to see your developments and your new products and services. And I'll put a link to the Honeybee Robotics website so people can find that. And if people want to learn more about this, there's your website. But if they have questions and they want to reach out to you, what's the best way to connect?
Oh yeah, people can reach out to me directly. I'm on LinkedIn, and Honeybee has an Instagram that I run.
Mhm.
So
Okay.
yeah, feel free to reach me on LinkedIn or Instagram. And yeah, I enjoy especially talking to small businesses, to students. I'm excited to talk to people who are excited about space and about the space resources economy. So anybody who wants to discuss sustainable, long-term space visions, that's something that I'm into. So
Okay.
feel free. Yeah.
Well, I'll put your LinkedIn profile link and the Instagram link in the show notes as well, so any of the listeners can find that. So I love this conversation. It's great to hear what Honeybee's done in the past and
Yeah.
what you're
Thanks,
working on
Steve.
now. It's exciting, and I appreciate you taking the time to talk with me today.
Thank you so much for having me. It's been great.
Thanks.